sure you know that. So therefore the only odd function that's in here, sine of x. So sine and tangent are odd, and so are the reciprocals of those two, and therefore cosine is the only even one, and its reciprocal, which is secant. Those are your only evens. ln problem. So all ln equations, you want to start with your domain. So the domain of ln's, in this case, this piece, the argument, what are the only types of values that ln will take? Positive. Will not take 0, and it will not take negative. So then you just take this piece, set it equal to 0, you get your x equal to 2, and then 2 is here. If I'm doing a mini sign chart for x minus 2, if I put a negative 1 million versus positive 1 million, ln only takes positive values. So based off of that, ln only will take this. This is not the answer to the question. This is how you start ln problems. You actually think about the domain of an ln problem. So that's the domain of the ln. Now I got to actually solve the equation, or the inequality, I would say. So I'm trying to get this to be by itself. How do I eliminate the ln? E, so you probably did this guy. And you get x minus 2 is less than e to the 0 is 1, and then you get that x is less than 3, but has to be greater than 2, therefore this guy. So that's one way to do it. Your ln problems, you have to think about your domain, and ln does not take 0, and it does not take negatives. How do we know that? Because we know what the graph looks like. So this one I thought was easy enough that you could do a transformation. I thought the transformation way was also a nice way. So this is what the ln graph looks like. Right? This point is at 1, 0. Therefore, if I was to do the transformation of x minus 2, which way does it move? To the right, 1, 2. So there's the new point. This asymptote, which was at 0, now is at 2. Here's the graph of it, and then it's asking where the graph is less than 0. The graph is less than 0 during this piece right here, which are only between 2 and 3. Okay? Right? Origin. And then even or symmetric about what? Yes. Your origin means flip it 180 degrees, turn the paper upside down, it should still be the same. All right, and then number 3, asymptote, so that should have been an easy one. This one is y equal to 0. You should know all your graphs, okay? You should know your graphs, and then you should know what the equation for the x-axis and y-axis are. All right, so those are done. At this point, I'm going to start going over some notes. You have some options on how you want to do this. If you look at that packet, there's a blank page at the front that just says notes. You're welcome to use that page if you want them in the packet. If you want to take your own notes in something else, you're welcome to do that. I would like for you to update your foldables. Meaning, we'll take some notes here. You should take back whatever is important from here that's not already in your foldable and put it in your foldable. Once you leave me, I'm almost 100% guaranteed that every single one of you will probably take a calculus class. I don't think there's anyone in here that's going to be like an art or a English major. I don't think. If you're in here, then maybe you'll be my one and only. But the majority of you want to be in some kind of science, technical, business major, and you all have to take calculus. That's what you should take with you. That foldable has everything in words that you understand, because in college you may not understand the words coming out of their mouths. They use big words and they don't translate it. I translate all my words, like top and bottom. It's actually that the fact that the function values are greater. Top seemed much more logical to you, so I use ways to try and translate it to you guys so you understand it. Some of you still don't understand it with my words. Can you imagine if I never translated it at all, how much worse it would be? So update that. Take it with you. If you go to BC Calculus, take it with you. Those kids say that that's one of the easiest ways to go back and try to find stuff that they're supposed to know or that they learn too quickly. Same thing for college. You'll have everything there in words you understand versus the way the professor gives it. All right, so here we go. We're going to go through, and this is pretty much the makeup. I'm going to leave some time to answer maybe a few homework questions, and then I'll go straight into trying to give you a little review based off of the topics that are written on the front. So we'll go through limits all the way to IVT today. So we'll start off with limits at a value. That looks like the limit as x goes to c of f of x. Other things, if you want to just listen, you're welcome to do that too, because you can always print this. The reason I say that, there are some of you, when you write, you can't listen. It's only one or the other. One piece of your brain has to turn off, so it's either mechanical or auditory. So I think the listening piece is also important. So if you feel like you can just print this out and you want to copy the notes later, you're welcome to do that, as long as I understand and you understand that you should be getting something out of this time. All right? So limits at a value, we learned a lot of different types of limits. The first type is limits at a value. That's what this means, that this is not an infinity. This is how we know it's at an actual value. We'll start out with the definition, which you guys should know. The limit as x goes to c from the left side has to equal the limit as x goes to c from the right side. And that limit has to be the same number. We'll just call it L. Squeeze my little if in there. So the left side, right side have to be the same. Then the limit actually exists, so we know that. The left side, right side being the same, there's only a few types of points that works for. So, all continuous points. Any graph, if there's nothing weird happening, every single point, guarantee the limit exists. So, take a parabola, I can ask you for x goes to 3, or x goes to -5, or x goes to pi, or x goes to e to the pi. All of those limits exist. Why? Because the function's continuous, has nothing weird going on with it. So that's the easy one. It also exists for removable. Those are the only two times that the limits will exist. Every other discontinuity, it's too weird, so the definition won't work. If you think about a removable, no matter what it looks like, from the left and from the right, this would be the left side, this would be the right side, they end up in the same exact place. That's what this definition states. So that's just limits at a value in general. If you're trying to solve limits at a value, the steps that you take, if I ask you limit as x goes to 2, what's the first thing you should try? Yeah, substitute, right? If I give you 2, try 2. If it works out nicely. So substitution is your first method. So substitution does not work. You get undefined. You get 0 at the denominator of the fraction. What's another method we could try? GCF, which is a type of factoring. Any type of factoring. Factoring doesn't work. What's something else we can do? Simplify. Simplify I put separately. They're considered the same thing, but I put them separately. Factoring for you guys, you sometimes don't consider that simplifying. Simplifying would be things where you might have to get a common denominator, and the common denominator may help to simplify out the 0 in the denominator of a fraction. So those are pretty much the basic ways, the most common ways. Lottie, stand up, get a drink, do something. Number 4, if those don't work, try graphing it. What do we know we have to graph? Absolute value. Don't guess on those. They like to use the absolute values because absolute value graphs can be tricky. Normal absolute value looks nice and easy. It looks like a V. But if I do something to an absolute value, I can make the function look really tricky. Step functions are another one. The graphs look a little tricky. Those are ones that I would definitely graph. And then all else fails. It's probably a rule that you just don't remember. One major rule that we know. Limit as x goes to 0 of sine of x over x has to be what value? 1. And you get tested on that. What if I change this value? What if I made that 2? Oh, no, not 2. Yeah, 2. 2 would work. 2. Is it still 1? No, because the rule says it has to be limit as x goes to 0. The other thing is that rule works as long as I take the sign of something over something. It's still going to be 1. So why do I do that? Because you guys see x, but what if that was x squared? What has to be on the bottom? X squared. If this is going to be 5x, then what has to be in the bottom? 5x. That's what I mean by the little smiley faces. They just have to be the same function, top and bottom. Okay? Argument and then the denominator. Alright, limits at a value. That should be pretty much a mini summary of what we did when we learned limits at a value. Then we're going to go into vertical asymptotes, which are also limits at a value, but they're just weird ones. Because a vertical asymptote happens when your limit as x goes to c from the left. So what happens if I'm at a vertical asymptote? If I come in from the left, I better be going either positive or negative infinity. One or the other. Okay? Or the other side. So the asymptote only has to be one-sided. That's the reason why I write the definition that way. Can you think of a function that has a vertical asymptote but only one-sided? Does not have a vertical asymptote. ln does. So ln of x, that function has a vertical asymptote, but it's only one-sided. It doesn't use both sides of the asymptote, but it's still considered an asymptote. Okay? So that would be a nice function to think about. Okay? That'd be a nice function to think about when you think about your vertical asymptotes. All right, to find vertical asymptotes. When you want to find them, there is a step that's really important first. Remove discontinuities. Okay, removable discontinuities, you want to take those out. And what you do to take them out, factor first, I guess I should say, and remove discontinuities, then take your denominator that's left over, set it equal to 0 and solve. That'll get you all of your vertical asymptotes. Let's do an easy one. So a lot of people will look at that and say, oh, it definitely has a vertical asymptote at x equal to negative 2. You have to make sure that you do your factoring first. Once I factor that out, what happened? I have a removable at x equal to negative 2, and I'm left over with absolutely no vertical asymptote at all. You can't be both. You can't be a vertical asymptote and a removable. Removables come out first. Okay? All right. And I know, I'm guaranteed, the limit exists at x equal to negative 2. Okay? What is the limit? Negative 4. Because I would use this guy that's left over to find it. All right. Vertical asymptotes. Good. Horizontal asymptotes. Okay? So horizontal asymptotes equals the same thing as end behavior. End behavior is the definition of the limit as x goes to negative infinity of f of x, and the limit as x goes to positive infinity of f of x. Horizontal asymptotes, the only difference, these limits will be a number. 5, 10. And those are your horizontal asymptotes. Horizontal asymptotes, you want to check both of these definitions. There was, and I gotta try to remember there was a test question, and I think this is it. And then they asked what if any are the horizontal asymptotes. Was that in your multiple choice set? Okay. Yeah, that question, that was an actual question. They ended up not counting it because too many people got it wrong. But now if you shows up again, they will have to count it because now they showed you the question. And they asked the question of what are the horizontal asymptotes. Most people did this. They did half of the definition. They never did the other part. It was a non-calculator, so you weren't supposed to look at the calculator and try to find them. It actually has two different asymptotes. If you substitute in infinity here and infinity here, it gives you, I think, -1, and if you put in negative infinity, that goes to 0, it gives you +1. So it had two different asymptotes. So this might not even be the exact question, but yes, I know the answer is two different asymptotes. This has two different asymptotes. Okay? I might not have written the exact same question. I can't remember. All right? Other things to remember about horizontal asymptotes, not only the definition, the fact that it is both sided limits and behavior, it's also the fact of if I ask you for rational functions, which is normally where you're used to seeing your horizontal asymptotes, that's when your function is a polynomial divided by another polynomial. That's the other time you see your horizontal asymptotes. I'm going to give you one way to do all your horizontal asymptotes. I used to give rules per different type of situation. Isaac, wake up. Okay? I'm going to give you one way to deal with horizontal asymptotes for your rational functions. Same thing as the limit if they ask you the limit questions. I'll show you that in a second. Pretty much, to find the horizontal asymptote or end behavior, circle highest power. In numerator and in denominator. Okay? You circle one or the other. Isaac, if you're going to fall asleep, then I want you writing so you don't fall asleep. All right. You just take whichever ones are going to be the highest. So, an example would be if I asked you to find the limit something like that. I'm not asking you for a horizontal asymptote. I'm asking you for the end behavior, and they would be very similar questions. So I'm actually going to answer both questions. First question is just the limit. Notice this. That means don't factor. That means do not simplify. That means do not sit here and try to substitute. If you're doing an end behavior model, then you circle the highest power in the numerator, the highest power in the denominator. That's the first piece. And then once you do that, I should have put it right underneath it. I ran out of space. Okay? Simplify and graph. So what does that simplify to? -2x cubed. And I don't care what -2x cubed looks like. I care that this is a negative odd function. Because every single negative odd function will graph exactly the same in the end. What's the easiest odd function we know? Even easier than this. -x. -x looks like that. I can do this limit problem the same exact way. So this limit problem says the limit as x goes to positive infinity would be this arrow, which means the answer to this question is -infinity. All right? What if I asked you the horizontal asymptote? You guys know many more rules for your horizontal asymptote, but that's actually the answer. There is none. If there was a horizontal asymptote, I would have a number there. The number would be 0. Or it could be the ratio. If the bottom power is greater, you know that one. Bottom power greater, 0. If they're the same, you'll end up doing this, and you'll still get a coefficient. -6/6, something like that. All right, rational functions, continuity, definition, write that down. You should know your definitions. See if you can write it without me writing it. one of the definitions. Some of you may use this one instead. So your definition states that the limit has to be equal to, what does that part of the definition state? The y value. So if you go back to that removable discontinuity, the limit exists, but because of that open circle, that's how we know that it's not continuous there, because the y value isn't the same as the limit. So that's why this definition will say why the removable discontinuity is not continuous, but every other point that's continuous, it should make sense. You're going to go to the point, but you're also going to be at the point. That's what the definition states. Continuity, if you want to prove it, because you'll have a lot of those piecewise functions. To prove it, you're going to need to know the limit as x goes from c to the left side. You're going to want to know the limit as x goes to c from the right side. And then you're going to want to know the y value. Those are the three pieces you need, which, same thing as what I had above. If you can answer those two limits and the y value, and they're all the same, then we have continuity. If one of them is different, it's not continuous. Okay? Any piece different can't be continuous at that point. And then IVT is the last thing. IVT, if f of x is closed and continuous, see, on the closed interval. I don't care about outside. I don't care if there's 30 vertical asymptotes that happen before A. I don't care if there's 30 removable discontinuities that happen after B. As long as it doesn't happen within the interval, then we're still good. If that's the case, then every y value from f of A to f of B is assigned an x value in A to B. That's officially what it says. Closed and continuous. I don't care what the function is that you decide to draw, but I could do the easiest one, which is just a linear function. I could do one that goes above it, goes below it, and then hits. I could do one that maybe only goes above but never goes below. Any of those, the theorem will work because it's continuous. I can even do a corner. I can do something like this and then jut over and put a corner right there, and that still doesn't matter because differentiability doesn't matter in the theorem. Okay? Gustavo, head up. So once we have this, the theorem says... Alright, so this is how high f of A is. This is how low f of B is. The rest of the theorem just says that if I pick any y value in between here, any y value, I am guaranteed that when I pick that y value, that there will be an x value that matches that y value from A to B. So this way. So it's kind of like this big little rectangle. If I pick any y value, I say this height. Because of the function being continuous and closed, I guarantee you that this height has to happen somewhere between A and B. Somewhere between here, it'll intersect that height. That's what it says. If you draw a function, any function, doesn't matter what it is, you can see that the theorem will work. If I ask you for that height, it happened right here, and look, there's the x value. If I ask you for a height down here, then here's the x value, and it happens within the domain. They don't care about outside. How do they test that? Show that there exists C such that that's usually what showed up in your free response questions. That's a y value. Show that existing or guarantee. Those are the words that should make you think theorem. Those are words that make you think the word theorem. that's how they would test it on the AP test. Alright, other than that, if you want to stay and finish